So for our last section here, we're just going to be looking at inverse of functions. We're going to be using some of the f of g of x and g of f of x information from last week. But just a little reminder, what is a function and what not is a function. All right, so if we have something like this right here, we have, it's called a mapping, where you just have these two circles. It's the same if I just listed 1, 4, 2, 5, and 3, 6. Just a different, visual representation. But we're going to be looking at if we want to find an inverse, which means it takes us back to where we started, right? What are the rules of when you can and can't do that? So when you can have an inverse, so if I'm what's called mapping, or moving 1 to 4, and I need to go in reverse, and I'm at 4, will I know how to get back to 1? Well, there has to be only one number 4 can go to. So as long as you have this bidirectional situation where this one maps to 5, and then 5 maps directly back to 2, right? Then we have an invertible function because there's no confusion. So as opposed to this, if I'm over here, map 1 to 4, and I map 2 to 4, if I'm on this side and I need to reverse it, I'm not sure which one I can go to, right? So if I have two choices, or if I don't have a unique choice I can go to, then it's not invertible. So this process of having just one to go to, 1 maps to 4 and 4 maps back to 1, that's called actually 1 to 1. So if all of the values map one number to one number and there's nothing repeating, you can definitely get an inverse. Right? Now there's a special language you want to use when you're justifying your answer, when it says justify or explain your reasoning, and that's probably the most pre-calculus part of this whole lesson, is just knowing what these explanations are. And you can say something like each output value, there we go, it produces or is produced by exactly one input value. That's a fancy way of saying 1 to 1. Every output has one input, so when I'm trying to reverse the whole thing, it's doable. Unlike that middle part, if I try to reverse this right here, I'm not sure where to go back to. Does this 4 go to 1 or does 4 go to 2? Right? So you could say the same sentence here, over here, right? And you could say, instead of exactly 1, each input, like you could say no, each input produced by multiple input values. Right? So we could say some variation of that and why it does not. Okay? Or each, another way of saying it would be each output does not map to a unique input value. There's many correct ways of saying the same thing. So you're going to see me write these in different ways and not just use the same exact wording, just so that if you read this in a question, it will make sense. We're not just used to one way of writing things. Okay. And a little reminder of what a function is not. You did this way back, I believe, in Algebra 1. Just what something, when it's not a function, is when you have two elements of the domain mapped to different numbers. So on the graph, you might remember this. If we plot these, 1, 4 would be like right here. 1, 5 would be right above it. 3, 6 would be over here. And this does not pass something called the vertical line test, because a vertical line touches more than one point. So if it does that, it's not a function and it can't be an inverse. Okay? So you can write that in there. It does not pass the VLT, vertical line test. And technically, you can have just a group of points. That's just called a relation. So you want to throw that in there, another vocab, and that's above as well. Something that's not a function, just a collection of points. You could think of it as like a scatter plot in statistics, like when we're doing our regressions. You might have 2 points that are right above each other in a scatter plot. Totally fine. It's not a function. And that's the reason why we actually draw a line of best fit. So when we have a line of best fit, we do have a function and we can work with it. And go a little bit deeper, since I know you guys memorized a lot of rules about what's a function, not a function. But I want you to understand why it doesn't function. It actually does not function. So I've been using an analogy here, like this is like a stock market today, like at 4 hours exactly after the stock market's been open, and you're measuring a value of a stock. And if you have 2 points that are vertically aligned, it's like saying, okay, that stock costs $20. Hey, and it also costs $25. The same stock at the same time has 2 different prices, which does not make sense. It doesn't function. So that's why we can't have this. If you're dealing with anything with time, like right now, if this was, it said, 2 o'clock, and the temperature is 73, and it's also 62. It doesn't make sense. The temperature is what the temperature is right now where we are. You can't have 2 different answers. It's not functional. So keep that in mind on why this vertical line test, actually means something and tells us that, yeah, you can't have 2 answers for 1 data point when we're talking about time. Right? So if you ever do an inverse and you get something that's not a function, then we do not have a inverse. All right, so we're going to look at finding these inverses many different ways, by graph, by chart, by table, all the different representations. Okay. And we have some new notation as usual. We have this new, when you find the inverse function, right? And this is a function that you can plug in your y values and it gives you your x values. And you actually verbalize this as f inverse. So even though there's a -1 there, when you're speaking this, you don't say the -1. It says f inverse of x, which is just returning you to where you started. Think about the function is you flying someplace. The inverse function is just flying right back from where you started. So you land at the same place where you began. All right. So we saw this before a little bit last week, that these will reflect over the diagonal. So if we graph the function and its inverse, there's a reflective geometric quality to it. So that's one way of doing it. You can see that these are both the same distance from the line of reflection. That's one way of finding the inverse, right? You could also, since y equals x and x equals y, you could take the x and the y coordinate and switch them, which is a little bit more convenient than just doing it geometrically. So all the coordinates will switch. And we know the notation is f to -1. And since the x's and y's are switching, that means the domain is going to become the range. So the range and domains also switch. The domain of the function is equal to the range of the inverse function. And vice versa. Range of the original becomes the domain of the inverse function. So let's do this graphically by using this y equals x line. And when you guys are doing your homework, you can always check your work by graphing the question. And you're going to be asked to find the inverse. You can also graph your inverse and then graph this y equals x line. And it should look like a mirror image. While you're learning this, it's a nice way of checking. Let me do this all the way from the beginning. This is 5, 6, right there, yeah. we go. Close enough. There we go. Right there. Okay. So we can see that these will be equal distance from the line. So at this point, we'll just map to right here. You could also just switch the X and the Y. Same thing here is another point here. That's going to be on the other side, equal distance to the line of reflection. I guess there's one right here. We could put right here as well. And right here we have 6, 1. So we can go to 1, 6 up here. So right here we can squeeze in our function. And it should create like a mirror image. You can say yes. And one way to know if what you just inverted is actually a function or it is a inverse is something called the horizontal line test. So you should if you draw a horizontal line through any of these, it should only touch the F inverse at one point. And that's the horizontal line test. So yes. And you could just use the same language. Each output value produces one unique input. Value produces one unique input value. And it's something you just want to ingrain into memory. We'll just use it over and over and over. Input. And again, another way of thinking about that is a horizontal line test. So this test to see if your inverse function is valid or not. If it doesn't pass that, then we got a problem. Alright, so let's try it with a parabola. We did it with this is a square root function. Let's try it with a parabola. So we can see this 8. Draw that in. There we go. And we're going to reflect it, or you can actually just exchange the coordinates. So 0, -2, -2, 0. We have these 2 points. I'm looking for lattice points. So since this point is actually on the line of reflection and won't reflect anywhere, so it's -1, -1, which if you switch X and Y is the same. But this over here, this +1, -1, will be up here. And then we'll go to the next, which is right here. So we can do the same thing there. It's on the line of reflection one more time, so we're not going to touch that. Do the one down here. And just carry on. We have 3, and -3, 7. And once you get all those graphed, we got this. There you go. So, is this an inverse, yes or no? So, one thing it has to be 2 things. It has to be 2 things. It has to pass that horizontal line test, which this does pass the horizontal line test, but it also has to pass the vertical line test. This is not a function, right? So, our inverse function has to actually be a function. This does not pass the vertical line test, so no. right? Not valid, right? So each, you say each output value is not produced by one unique input, or you could say, not a function. So it has to be one vertical line test and horizontal line test. Has to pass both. So if we can remember that graphically, we're in good shape. And then you can start thinking about, well, what if you didn't have a graph, right? And you only have the coordinates. Well, that means some x's will be repeating. So we can look at it different ways. We'll get to that a little later. Okay, so we got that down if we have the graph. Next is, what if you just have the functions? How do you tell their inverses without actually graphing them? So we did this a little bit last time. Okay, and let me show you, well, what if you're not given like g of x? How would you find out what this is? You're just told this. So if you're given a function and not its inverse, and you're asked to find the inverse, so if this said find f inverse of x, here's what you do. You take the original, which is y equals 4x plus 3, and you actually switch, since x equals y, we actually switch these. So those are going to switch, because the domain becomes the range, and the range becomes the domain. So the x's and y's actually switch. And when you solve for y, because we only know how to graph when it's y equals, that's when we get the inverse. So if I did this, I'd get x minus 3 equals 4y. Divide both sides by 4. And you can see, there we go. And that's where this g of x comes from over there. And we would say, okay, x minus 3, we're claiming that's equal to the inverse of f. So we can always find the inverse if we're given one function. And sometimes it's a little tricky to do the algebra, right? But there's a way to do it. Okay. But if you're given the two functions, we're going to go back to what we did last week. We're going to find f of g of x, and we're going to find g of f of x. And if they both come out to x, right, they both come out to equals x, which is that line of reflection. So on graphing, y equals x means it's the inverse. When you're doing the equations, you'll both get an answer of x. So if we do this carefully, we can show that. So here we'll have g of x is going to be plugged into f of x. So this is the g of x, and we'll plug that in for that x. And then we'll do the reverse. Just like last week. And then on this one, f of x is going to go into side g of x. So this whole part will go into this x. And simplify both. Force cancel. That equals x. Over here we get 4x over 4, which equals x. Hey. So that's what we did last week. Just the skill. Now you need to know the explanation. So again, like that other quote that we're going to use over and over, each output value produces one unique. So this is something you kind of need to know how to say this. Well, what's the conclusion? Justify your answer. You did this. We show that these two, right? These two are equal to each other. So we say since those two are equal to each other, and you got to write it out. Don't shorten anything. Don't leave anything off. Since these are equal to each other, which they equal x, then this second function is an inverse of the first function. So the second function is called g of x, and we're saying that's the inverse of the first function. So it's equal to the inverse of f. Now, what I just showed you on the left-hand side, I did this kind of on the side, very, off to the side, not the main part of the problem. But you're going to be doing this a lot on your homework. This is going to be one of the main things, a lot of algebra and solving. You have to do square roots and squaring and things like that. But, just so you know, that's one of the main ways of finding an inverse. Switch the variables, solve for y. And at the very end, you switch it, you'll have y equals, and then do write that next step where you say f inverse equals what you just figured out. All right, so let's go on to just charts and tables, and then we'll be done. So we're just doing the same problem over and over, just with different representations. We did it with graphing. Here's with equations. Let's do it with tables. Okay, which this is probably the easiest of all. We have a function. The table gives values for invertible functions. So it actually tells you it has an inverse. You don't have to worry about anything not working or not passing vertical line tests or horizontal line tests. It already tells you it's going to work. So what would the table be? X's become Y's, Y's become X's. So we could just switch the X's and Y's, and that's it. So this is the most straightforward type of showing of inverse, is just switching the X's and Y's. And you do not need to worry about putting into ascending order. Usually the X's are always going up, -4, -2, 0, 2, so on. It's okay that these are 7, 1, -5, and don't worry about rearranging these. So the X's become the Y values, or the inverse functions. And that's it. How nice. All right. So let's try another one. Right below it, it says the table gives you the values of h of x, y equals h of x, and it says this time determine if it has an inverse. So now we don't have a guarantee. So ask yourself, is this reversible? Is this invertible? All right. So what we're looking for is in an inverse that each x has one unique y, that one-to-one feeling. So if I had like this a -4, well, this x would go to this y, but it also has it over here. So that would not work. So in other words, if there's a y that repeats, you don't have an inverse. So you're looking for a y repeating. So down here, you can see, scan them, and you can see, well, -3 maps to 4, and 1 maps to 4. No good. It's repeating. So this is equivalent to where we started just with the mapping. We have two x values mapping to 1. So if we try to reverse this, we don't know where this 4 should be going, the 1 or the 2. So realize this is the exact same problem as this, just in table form. Okay, it's just different representations. And we also have -2 is mapping to +3, and 0 is matching to +3. So for those reasons, h of x does not have an inverse function. There are output values of h of x that are not mapped from unique input values. So go ahead and write out your reasoning using this kind of language, using this. And you got to find your tone and kind of get practice at that, so you have that locked and loaded when you need it, how to say that correctly. And it has two questions, or two statements. Determine if h has an inverse function and give a reason for your answer. It's a good idea to answer those semi-separately. So answer the first one. Say no. Start off with that. H of x does not have an inverse function. All right. And then give the reason for the second statement. give a reason for your answer. You could say something to the effect there are output values of h of x that are not mapped to unique input values. That's a fancy way of saying what we just did up here. You want to think about, if I get to 4 and I just have 4, we don't know where to go back to. If I have a 4 and I'm trying to reverse it, do I go back to -3 or do I go back to 1? We don't know. So that's the dilemma, that's the problem. That's why we don't have an inverse. We don't know where this 4 should really go because there's 2 numbers it came from. If we had one number, like it was 1 to 1, then we'd be okay. We don't. And lastly, we just have some tables, so some evaluation work. Now, when you have inverse functions, remember the x's and y's are now switched. So when we have an f inverse, that means we're going to look up this number in the y. And we're working our way backwards. Remember, getting there is x to y. The inverse is getting home, going from y to x, going back to where we started. Right? It's like flying from here to Hawaii. The inverse is Hawaii back home. So we're starting like we're already there, and we're just doing the return trip. So the -4 should be here, and we're going back to where we began, which is 5. And we can do some nested functions. This one is just g of 1. So do it normally. So that would be, look in this column. This is g. Look here for 1. That's like flying to -3. And then this says, well, let's reverse it starting with f. Start with 3, -3, like you're already there. And fly back home to +3. So try those last two, B and D. Check when you're finished. G right here. -1 goes to 4. All right. Check those. What do you think? Are we okay with this? All right. So those are inverses. We'll do part 2 tomorrow, which will just be more fraction and equation work. But this is the nuts and bolts of finding inverses.